Hi, Jim Shaw from Crystal Group here. I'm here today with Matt Seibert, and we are talking about liquid cooling. And one of the things that we probably should do just a little bit of a background on is why are we talking about liquid cooling in industrial servers or military servers? Because generally electronics and water don't mix very well. And I think what you find is that the power densities have become so great that a lot of the previous techniques no longer work. We can't push enough air past, or it requires so much surface area to cool these devices. It used to be that you could do some custom heat pipe designs. This is one from one of our previous designs, and that worked, but not so much anymore. Matt, what's your impression on the way that the heat flux has caused us to kind of driven us, if you will, into this direction?
Yeah, so what we've seen is that over the years, the heat loading has become so great that conventional, heat sinks, like Jim was saying here, just don't work. We can't get all of the heat just up these heat pipes and out to a cover. We actually have to take the heat to a bigger surface area, something like a heat exchanger like this or like this. So what we're doing essentially is we're running coolant over the top of the components, and we're using a heat sink to then pull that heat out of the components and transfer it over to a heat exchanger like these here.
Oh, and one of the things that we've struggled with is really the heat loads are so great. Like these NVIDIA cards right here, that might be pulling 350 to 450 watts. And so we've actually had to design our own heatsink assemblies where we're creating essentially water blocks that go and then bolt to these specific components. Matt, what are some of the things that you think about when you're designing a water block like this?
Sure, so some of the things that we got to think about are, where are the heat loads, what components do we need to interface with, and then how are we going to get that heat out, and what are the flow rates and pressure drops that we have to be concerned with. So with any of these designs, space is always a huge consideration. So what we run into is we're often trying to fit cards into a smaller area than what they would be when they're air cooled. And that leads us into creating channels and different geometry here that could create pressure drops and create situations where we wouldn't be able to get proper flow through the heat sink. So there's a lot of different simulations that we go through and a lot of different techniques we use to be able to then generate lower pressure drops.
So to kind of summarize that, especially for GPUs, you can get an off-the-shelf heatsink assembly that blows air through the system, but you're going to be limited in the maximum ambient temperature that you can provide full GPU inference or machine learning. So one of the things that liquid cooling provides is essentially an extension of that ambient temperature performance. And it's not just GPUs, is it, Matt?
No, so this is one of the designs that we've come up with for a dual socket CPU motherboard. Now, as you look at this design, you'll notice that we have incorporated both CPUs into one design. And what that has allowed us to do is it's eliminated some fittings and some different interfaces so that we can eliminate risks of leaks and that we can make a lower pressured system overall. So this, with the new CPUs, we're seeing wattages of, 265 watts per die. And that's creating, issues where we can't cool that much heat in a typical 1U or 2U system. So now we're pumping it out to a system like this that allows us to dissipate that heat more effectively.
Ah, good. And this technology isn't limited to just CPUs and GPUs. I notice over here, Matt, that we've got a power supply that we're doing liquid cooling on. Can you tell us a little bit about that power supply?
Yeah, so over here you can see this is a Crystal Design power supply, and this is specific to our ABC, our autonomous vehicle platforms. And what we've done here is we're actually plumbing fluid right over the top of the bricks to help dissipate some of that heat off of the power supply itself. Now this is handy in a situation where you don't necessarily have fans or air over component cooling, so that way we're able to take that heat and then bring it outside to a different area of the vehicle or a different area of the system to help us dissipate that heat in a more accommodating way.
And one of the things that's kind of key to our ability to do this is putting fittings in that don't leak. And we've certainly learned a lot about that. You want to describe a little bit about the things we do, Matt, to make sure that we've got liquid tight fittings and a good design?
Yeah, so over the years we have gone through different variations of different types of fittings. What we found is we've moved to a much more rugged industrial type fitting here. And those fittings are much less prone to leaks than what you see in the standard commercial quality type fittings. We had been in that market for a long time, and what we had found is that they just weren't reliable enough for what our customers would expect. So we've gone and we've switched to fittings that are more industrial. We make sure that the hoses are rated for well above any of the pressures that we would see, and that their leakage rate is really, really low. One of the other things that we've gone through over the years is different types of quick disconnects. So this is how you would interface one of these radiators to our system. As you can see, these units here have quick disconnects on the front of them, so our hoses would run in between, like this unit here and then this pump unit here. And over the years, we've seen different types of quick disconnects that just haven't been able to live up to the rugged environments that we're used to seeing. So we've gone to a much more high-end type fitting than what some of the other markets are using in the liquid cooling electronics.
Yeah. So one of the big drawbacks on this is pressure drop, right?
Correct.
So you give up a certain amount of pressure drop when you go with these fittings, but tell us a little bit about what's different about this fitting than what you might see in a rack environment with respect to leakage.
Sure, so one of the things that you would see here, so talking about pressure drop, so you do run into what essentially you're doing is you're creating a shutoff here. And by doing that, you're adding a bunch of right angle turns, and those are high pressure drop environments. So the difference between what you would see here and something that you would see on a rack is that the rack fittings are generally designed to be high flow, low pressure drop. And we're willing to accommodate that higher pressure drop just to be able to make sure that we're not going to see leaks inside of the system or leaks in the field.
And that's leaks when you disconnect also, so those are, what do you call them, no drip,
yep,
right?
No drip or no spill.
Yeah, so and that's very important to our military and industrial customers. So that's a kind of a good overview. Crystal Group, is well positioned to be able to create these custom heat sinks, and Matt is the engineering manager over the mechanical team for doing that. And so what we can do, coupled with the capability of the engineering team and the fact that we have inside the facility 18 CNC machines to be able to really kind of create this kind of product, it gives us a lot of flexibility. And so with Matt's help, we're really able to serve the market very effectively. And so that's one of the key benefits of coming to Crystal Group that really makes the difference. So thank you very much, Matt, for your time. And if you have any comments or questions, please drop us a line. Visit us at crystalrugged.com and give us the comments. Thank you.